Okay. Welcome back to Old School Coding. We are still working on the 8224 clock generator and driver. I did what I thought was the implementation, and I am now verifying it by writing up some coding and testing it. So far, we have verified that the reset signal is latched properly and the ready signal is latched properly, at least for the common case of going from off to on, reset falling and ready coming active. And I'm going to pull a programmer proof. It says, I know that the code doesn't have any things in it that differs based on going high or going low. Well, other than we have this reset rise. Well, we aren't using these yet, but I do need to, these are badly named. This is I224. I'm going to put BIST at the front on reset rise. This is a BIST function. Oh, come on. And same thing with fall. Okay. So we do have something here that says on reset rise and on reset fall, we're manipulating the status strobe. And again, I'm pulling a programmer proof that says that rising and falling are going to be very similar. And this only happens here in case 4 as a result of these things changing. And other than that, status strobe is doing the right thing. So we did not check, however, with sync, nor did we check the number of edges on status strobe. So we're going to grab this instead of phi 2. We now have counts of phi 2 going up and down. Now, all during this time, status strobe was forced to 0 by reset, right? Now, it should have gone high when reset was released. And I noticed that it didn't. So we actually have found our first culprit. We're going to assert, oh, we're going to add more stuff below this. So let's put these asserts above it. So this is saying, we get to here, we apparently had 8 rising edges on the status strobe, even though we didn't do anything with sync. So I am going to come in here and I'm going to assert that sync is low. All of that time. Now with sync low, the status strobe should never in fact rise. No, it should rise once actually, and should stay high. So let's take a look at our status strobe stuff. So we initialize it, we set it low. Here in case 1, we are going to set it to the reverse of reset. So if reset is low, we are going to set it high. It's going to stay high but it's never going low again, so it should never be seen to be low, so we never should see a rising edge, which means that we should only get one call to our rising edge thingy. We should only get low if... so, yeah. All these edge high and edge low are fine, but all these places where I look at the value, I need to look at the value, not the pointer. That was a bug. So starting here, this is where it goes high. Okay, so this is when reset in is released. The status strobe is going to go high and it's going to stay there until I start getting sync pulses. Okay. Now, if I were simulating the CPU, we'd actually get a sync pulse as we come out of reset, and then no more until ready came out, and then when ready went high, we would then continue normal operation. But what I'm going to do is I'm going to come down here, and I'm going to do, okay, simulate a few 8080 instruction cycles. Let's say 6 cycles. Now, as part of that, what we're going to do is we're at the beginning of the M1, the machine cycle 1, tau 1 right here. And what I want to do is manipulate sync so it looks like what the CPU does, roughly. So according to the document, let's bring this up. So what the 8224 says it does is it says it's raising sync here shortly into phase 2, and it's going to drop it sometime later. So it's going to keep it high for an entire T state. Now, normally, I think what I ended up doing when I was roughing this out was sync rose on phi 2 rising and it fell on phi 2 rising on the subsequent thing. Let's go roll it back, and I'm going to take a look at the actual CPU timing diagrams. So here is let's pick one that's good. Here is a typical machine cycle with a wait state. Notice the sync is rising here during T1, and it falls at roughly the same location during T2. And the important thing is that sync is high during status strobe, and this shows it as being sampled during phi 1, when in actuality it's going to be sampled just before that. So I'm going to tie sync to phi 2. Actually, before I do that, though, we actually have a real data sheet for the 8080. Scrolling it forward here, it's just beyond the 224 and the 228. So here's the actual data sheet for the 8080A. I notice it does say 2 microsecond instruction cycles, so this is the 18 megahertz clock thing. And we're looking for the actual time of the sync signal. Now we see here that it rises TDC after the rising edge of phi 2, and it falls TDC after the rising edge of phi 2 here. TDC is at most 120 nanoseconds, which means it is somewhere between 0 and, well, 120 is 2 oscillator cycles. Okay? So 2 phases. So we're somewhere between, this is phase 1, 2, this is phase 3, this is high. So phase 3 or phase 4. So The CPU doesn't receive any signals other than phi 1 or phi 2 for signaling. So in the simulation, we're going to have to tie sync to phi 2 because we don't get more oscillators coming in. Literally, the CPU doesn't have pins for it. I'll show you. So here's the input pins. We've got phi 2, we've got phi 1. We don't see phi 1a or anything else. All of these are just things that get sampled on those edges. So basically, the hardware is doing this at an offset from phi 2 rising based on internal logic delays, not based on an edge happening later. So I'm going to tie this transition to this guy rising. I'm going to start doing that here in the test. Boop, you go away. So in order to do that easily enough, what I'm going to do is I'm going to have a little test code that says post on phi 2 rise. And we're going to say if under certain conditions, what I want to do is on a phi 2 rise, raise or lower the sync. So we're going to do static. Well, this guy owns what t state of the cycle we're in. So we're going to have a static int t state count. T state equals, say, 0. Phi 1 rise marks the start of a new t state. So we're going to come in here and we're going to say t state equals t state plus 1. We're going to go 0, 1, 2, 3. Actually, we need to go 1, 2, 3, 4, 1, 2, 3, 4. Okay. So phi 1 rise, we're going to advance the t state number. In actuality, we have 1, 2, wait, 3, 4. But that will happen only when we start to actually have a CPU that responds to wait states. For testing the 8224, I don't need to worry about that because we don't have visibility into any of that mechanism. So I'm just going to start issuing sync pulses on the appropriate t state. So phi 2 rise, switch t state. Case 1. Gen arrow sync. Actually, this is the sync. We own sync, so we can say that. So edge high sync. And t state 2, edge low sync. And what I really want to do here is if gen arrow reset, arrow value, t state is equal to 0, else that. So t state number 0 is I'm in a wait state. And we won't come out of wait until reset is done, and then we'll step to 1. The real CPU has a bit of a delay in the middle there, if you get what I'm saying. But reset will come and be recognized in the middle of a state. And this says the next state we go into, we will see that reset is gone, and we'll lift it. But we can actually assert t state up here if we want to. So as of when reset changes, we should start getting sync pulses. And actually, what I'm going to do is wrap all this together in a loop that says for certain iterations, we're going to do things. So we will call this we'll do machine cycle whatever. This is going to start machine cycle number 0 for int m cycle equals, let's do 1. Come on. No, too many of the asserts are going to change for me to do that. Frick. Change reset. This is where sync is going to start to move. And it's going to start moving. Yeah, I need to do it as a loop with some asserts. So we're going to assert this afterwards, but I'm going to do this by saying I'm going to do an expected thing here. This is bit expected res in. We're going to go to that. We're going to say doom. So we'd have these expected values. So I just need to manipulate expected when things change. So for each machine cycle, we're going to check to make sure everything is as expected, and we're going to let the clock run out for that machine cycle, and we're going to go back up to the top. And now we start folding in the rest of this logic. So after we do this, after we do the switch, yeah, but after we've asserted the conditions are correct, we're going to switch. So this is going to be stuff I want to happen during a given machine cycle, and I'm going to let I'm going to start at 4 here. 1, 2, 3, 4. So we're going to run a few, and then we're going to do something. What we're going to do in cycle 4 is we're going to do edge high, res in. We're going to say expected res in is equal to 1. Okay, and that means that once we have done this clock cycle, the next time around, we're going to expect reset to go to 0. I'm going to abort there because I want to just see what's going on so far. Oops. Okay, so these guys aren't being used yet. That's right, I didn't set these up yet. So post on phi1 rise. think that's right. And I'll hook up to the BIST functions while I'm developing this, but I will have to kick those out. Those are reset rise and reset fall. They're called I8224 BIST on reset rise. Okay. Which means that at some point STSTB started moving. Well, that makes sense. So we get into M cycle 5. So 4, we released reset and we ran until, and when we came back around, we saw that STSTB, as we transitioned, it was the other value. So it went high. That makes sense. And sync will have changed. So from here on, we want to do syncs. So int sync on M cycle phase equals -1. I think it's every fourth. Yeah, so we're going to do a default here. Expected sync is equal to 0. We'll just have to do is we'll have to set sync high on the cases where we want it high. So sync on cycle 6. That's better. Set it on 5, so at the beginning of cycle 6, it's set here. It might be more interesting to instead put this after the run until, so we set the conditions here, we do the run, and we test the conditions down here. So STSTB doesn't move until, so STSTB doesn't move immediately. So we're going to at the beginning of t-state 4, we are releasing res in. By the end of 4, reset will have been cleared, but status strobe will not be released yet. Is that right? Nope, that's correct. Status strobe is still low. No, there we go. Okay, so cycle 5, at the end of cycle 5, sync will be the other way. Okay, so 4, we released res in, we get a status strobe going high by the end of the cycle. Now STSTB is being lowered during the last little bit of the cycle, and it's not being raised until the start of the next cycle. Okay, we're going to use that for testing here. Now all these asserts, there. That's better. So, at the end of cycle 5, we were still expecting sync 0. It's 1. Well, it really needs to be 1 at this point. And STSTB is actually 0. So during cycle 5, we are going to flip sync down, or flip sync up, and at the end of it, it's going to be getting a pulse of STSTB. And cycle 6, STSTB will have returned to 1. Basically, I'm looking at the expected value, the values in the error, and I'm saying, is this sane? And sync will be 0 again. So CPU will hold sync high for 1 cycle, which is middle of 5 to middle of 6. So at the end of 5, it's going to be 1. The end of 6 is going to be 0. And the status strobe will only be 0 at the end of when that's there. So now we get to 9. So 5, 9, and so on. So if M, so really we have expected sync is equal to M cycle mod 4 is equal to 1. And expected STSTB there. Now, as long as you don't get back to reset, these are correct. Whoops. So we want STSTB to be 0 until M cycle is greater than 4. And once it's greater than 4, it's going to be we are, hold on, I shouldn't have gotten rid of these cases here. Let me, okay, so sync. It's going to be 1 when at 5 and so on. So M cycle greater than 4 and M cycle mod 4 is equal to 1. STSTB is 0. Oh, it's less than 4. Equal to 4, it's going to be 1. There we go. I'll write these both as greater than or equal to 4. And there we go. So that checks our sync behavior. So now ready in. I want to run this for a bit, so we're going to start at case 12. We're going to edge ready in, goes high. And let's look at what changes. Well, yeah, expected ready in. So we do that, it's going to do that. Okay, and we're going to run this out for 50 M cycles, and the counts are going to be wrong. So observed count, well, observed count of 50 makes sense. So we'll get 50 rising and falling edges of phi, because we did 50 cycles. Did the one up here followed by the rest of the 50. And STSTB, we observed 12 of them. I think they're both 12. Yep. So it started at low. Yeah, at the end of the last cycle that we execute, I believe we leave it low again. Let's bring this up to 52. And we get a rise. There we go. So it started out low. It's going to end up high. We're stopping kind of in the middle of a machine cycle. In fact, let's do 53. So there's post. We're going to make it quieter and smaller, and then we're going to make it expanded for BIST. And yeah, I think I am going to run this whole thing, this many cycles, for power on self-test. Built-in self-test, we don't need to print. End of machine cycle. So I was going to print something interesting on BIST reset, rise, and fall. That's right. I wanted to check what T state I was in and what phase I was in of the clock. So we're going to printf oh, and I'm not using gen, so leave that in place. Okay, so we have exact numbers here for reset falls and ready rises. But I need to print let's see. So what else do I want to print other than reset and ready? I would like to get, as part of BIST, we'll probably reduce the number of loops we do because I also want to see other signals. Check the timing on everything. So we output phi 1 and phi 2 as well, so we're going to print those. And let's see. Phi 1, phi 2, ST, STB. That is active low. So the important outputs are phi 1, phi 2, ST, STB, reset, and ready. Okay, so that will give me a trace of all of them, and I will have to examine those numbers and make sure that they are in fact correct before I assert that matching them is perfect. Now, if each edge carried its own name, then I could pass in the edge instead of the gen. I could print the edge, I could print the edge value, and all of these functions would become one thing. But edge doesn't currently carry its own name. I could change that. So let's take a look at our log. So I'm noticing that 15515 1923. Why don't I print, instead of this, I'm going to print an elapsed time. Instead of T0 plus percent %LLD, I will print percent 8.3F microseconds. And now instead of tau minus T0, we're going to call into clock. And this needs to be tau minus T0 becomes clock elapsed ns of T0 tau. And that's going to return nanoseconds along its floating point microseconds to divide by 1000.0. Okay. So phi 1 is rising 27 nanoseconds in, so we're getting a single oscillator tick before we see phi 1 rising. Fudge. Not the initial conditions I wanted. But anyway, rising to fall time. This is 111 nanoseconds. That's good. You know what? If I run this at 20 megahertz instead of 18, I can develop this better. Hold on. I did not change anything that should have changed the expected value of sync. I don't understand. Oh, right. I'm stepping forward by 500 nanoseconds when it needs to be 9 times the clock period. So, tau m cycle time equal to something. So in test init, we're going to be so if the frequency is that, m cycle nanoseconds is what? So there's the oscillator period in nanoseconds. I need to do that by 9. Okay. So that does the math correctly for 18. And now if I do 20, there we go. So now I just need to make those global, and we're going to do osc frequency hertz. The things we go through because we overspecify in our tests or use magic numbers in our tests. So now we can use this. There. And now I'm no longer dependent upon 18 megahertz. What? What features? Okay, I just had an extra parenthesis in there. And it'd be even easier if I use 10 megahertz in, no, where to go? I'm going to use a 10 megahertz crystal. even easier. So we can see that that is 2 clock phases. We're still got this half offset. Damn it. Like it's doing it on the second edge. Okay, I am going to switch forward here and do that. Moreover, I am going to move all of this stuff up as far as it will go. So everything should have gone down by 1. So phi 1 rise should also have gone down by 1. So there's something weird going on here. Okay, state is garbage. That's really bad. Oh, duh. Helps if I actually look at my compiler warnings before I look at the test errors. Okay, so all of these guys are now goes from 53 to 52 because we're doing 1 fewer inside that counting area. So we are indeed at loop top where state is 2. So we're at state 1, and we're at state 1 again. Oh, I'm pre-incrementing tau, aren't I? Yes, I am. I need to run the stuff for the given tau and then increment tau. How many off by 1 errors do I have here? Nope. Let's not adjust that. So clock run 1, we're going to increment tau and then execute the stuff for that tau. So we will not have incremented tau until we decide to do a clock tick. Okay. Which means that we're starting here at T0, and the first cycle is going to happen at T0 plus 1. Which means that if I want this to be 0, I want to be T0, comma, actually I want it to be, yes. We expect to run, not where it runs, we would measure that. We expect to run one at T0 there. Okay, so that works out neatly. That says that we rise phi at plus 0, plus 0.2, we fall at plus 0.2, we rise 2, and plus 0.7, we do that. So all these line up, but of course, phi 1 to phi 1 is 0.9, which is kind of ugly. So we do know that these are right. I can gauge the rest by eye based on that. So instead of 10 million hertz, I'm going to go to 18 million hertz. Oh, let's go to 9. So 027,127, yeah, that works. That actually is nice because that gives us at the entry to phase 2, at the entry to phase 7, so 0 is 9, so 027. So essentially this is the end of 2, end of 7, end of 9 is 1.0. Okay. So we get phi 1 moving up and down nicely. Then here, during this cycle, phi 2 rises, and then very shortly after that, STSTB rises and reset falls. So reset falling, change STSTB. And those are not in the order I expected. Oh, right, because reset was told to fall, it told STSTB to fall. Then the STSTB viewer saw STSTB move, and then reset finally saw reset moving. Okay. So reset moves STSTB properly. Boom, boom, boom. STSTB is now going to pulse during the last bit of the cycle. Last 110 nanoseconds, yep. And it pulses again here at before 9. And it pulses again before 13. That's 4 microseconds because I'm only running 9 megahertz. I should be seeing status move. Oh, I'm not monitoring status. Let's monitor status. Why would I say stat? It's called sync. So we can see where sync is rising and falling here, separated by the t-state. Okay. And my easiest way of validating that sequence is to put it in the text file and make sure that each run has the same value. Okay, there we go. And we have locked down that set of outputs. Next thing, do I want to have every edge contain its own name? It means everywhere I'm creating an edge, I need to, as part of its initialization, include the name. When I'm creating an object contains edges, I want to update the name of the object. I think so, but I think I want to check in what I've got so far and then make that change. So let's see, do I have to get cracking up? No, I don't. I don't often use GUIs, but in the case of Git, I'm willing to do that. So this is, do a real quick git commit here. Mainly this is add I8224. Also, add edge underscore 2, EV1. Use it for edge high and edge low. I'm reading you what I'm typing because I'm not putting it in the recording. I am going to discard the hunk that tries to help the debug I notify wait. I'm going to figure that out offline. I'm going to add the 8224 stuff. Use, okay, so for test for BIST of 8224, print timing of signal changes to log, use diff log. Log must be same for pass. Okay, in the README file, I have added ref to add link to 8080 MCS into again README. Add assert any integer macro. Update expected output from BIST. Okay, that's snapped. Next job is making edge contain its own name. So top of edge, we're going to say CSTR name. And edge init is going to take a CSTR name and I'm going to provide a macro called edge init that calls edge init with the edge and with the symbol. So if you define something called foo, you say edge init foo as a macro, it's going to say, oh, foo, and set name to foo. So in var, I'm going to demand we have a name and that it is not blank. This is going to kick off in a lot of places now. So now if we have an edge pointer, then we can get at its name. Well, we will when the compile finally gets to where it's working again. Okay. So this edge is called, well, let's just call it E. A lot of these are just going to be this. Okay, the easiest way for me to do this is to pull out pointers. Like I do this in a lot of my code where I will pull out the pointers properly. Okay. Yeah, better do this now than later on when I've got a lot more edges in the system. So now, in theory, I could do static void edge change. So we could say at that time, time and whether it's high or low, so E arrow value followed by E arrow name. And all of these, well, almost all of these go away. log and expect it up to the top, compare windows. So basically I changed the form of the output. I better make the form the same to verify that it didn't change what it says. Nope, that's equivalent. Okay. So BIST and now bench. Bench is going to be just like BIST, except it's not going to print anything or test anything. So initialize. We aren't going to count rises and falls. We aren't going to check changes. We aren't going to print changes. We aren't going to insert stuff. Since I am benchmarking, do I want to have some subscribers? Well, let's benchmark without subscribers first. Now, what are we calling in with here? Find out in a moment. We are going to run a fixed number of cycles. For each cycle, we're going to do a clock run until. Okay. Let's run 1,000 machine cycles. And we're going to do this little flip of calculating the future tau and running until that future tau 1,000 times. So I suspect that our main loop will be doing something similar to this. This may be overkill, and maybe we can reduce the cost of it. So this value here is going to be how long this whole thing ran, which is 1,000 DEM cycles. So each M cycle I'm gonna print out. So you know what? Test M cycle M and S. I don't trust that this is going to be the right value. No, that's a nice integer value for what we're doing. Put this 1800 again. So we're going to do that times 1,000. So the number we're going to get here is the time it takes for us to execute an M cycle with absolutely no payload at all. Oh, all the numbers changed because I went from 9 megahertz to 18 megahertz. Her to her. So it takes us 99 nanoseconds to execute a whole M cycle of nothing. I don't know if that's good or not. So that's nine oscillator cycles, each one of which is taking 11 nanoseconds. So what we're saying is stepping through this for all 9 states is taking 100 nanoseconds. And the real CPU does it in 500 nanoseconds. And I know elsewhere we can go quite fast, a little faster than this. So I'm still not as fast as I could be. But I think absent profiling, I'm not going to find out where I've goofed up. Okay, so going for 10 times as long, we only went down to 79. Go for 100 times as long, 78. So yeah, really. We're going to accept the new output since it's just half of the old output. So about 80-ish, varying up and down pretty widely. Oh, we're also in reset, haha, which means that what we want to do inside the bench is a little more than that. I want to run an M cycle and reset. I want to release reset. I want to run 3 M cycles. And then I want to release ready. And then I want to run a huge number of M cycles. Minus 1, 2, 3, 4. And really what I can do here is that, and down here I will just say run until final tau. So 80 to 90 plus. These numbers are bouncing around quite a lot. I think in the interest of understanding what's going on, I'm going to temporarily multiply that by 100. It's going to take a while to run these benchmarks. This also means that if my CPU is being clocked up and down by the operating system based on load, it means that we're running things longer, and it will tend to clock it up to where it's sustained. In fact, I'm seeing the CPU get hotter as we go. Still not too hot, but warmer than it was. So about 80, okay. I still think that there's something else going on inside this. It'd be a shame if it was all those extra tau increments. I've got to try something. What if I don't increment tau there? There's going to be hazards for the clock, which means edge 2 needs to ignore if it's the clock. Oh, this is time critical. Which means that these asserts are costing me dearly, because they're going to trigger off, and I would have to add a whole bunch of extra stuff. Oh, I know what to do here. I'm going to special case the clock. So instead of doing that, I'm going to say clock arrow value equals 0 right here. So we are only getting edges that are rising on the clock. I'm going to assert that T1 is greater than T0. And I'm going to assert that T0 plus T1 minus T0 times 36 is equal equal to tau. Oops, no, I'm running to plus 32. I can plus 72. I still say plus 72. Right, future tau doesn't know that the 2 is there. Fortunately, I explicitly put in 2's. Okay, these still work because it would have been, well, no, let's say 2. Yeah, there we go. Okay. So by incrementing tau only once, we've gone from 80 to like 60. Okay, I give up. Tau's going to increment by once. Our clock only has rising edges on it. It's special case. It's not a real edge. That's fine. It still does everything we want to do. Okay. The things I sacrifice for performance. It just means that if we are going to print something and I want to have 2 ASCII cells per tau, then I just need to have the first one be rising or falling edge, followed by the second one being either hold high or hold low. Good enough. And it means that if we are logging the oscillator, we will see a constant stream of rising edges with nothing else. But with 60 to 70 nanoseconds of overhead per machine cycle and trying to be some small fraction of 500 total, we're still doing pretty good. Although I'd love to be able to peel out more. To do more, we need to do profiling, and I think that the high levels of optimization we're using kind of make profiling hard, and if we turn off the optimization, the profiler is going to point at things that get optimized away anyway. So we will have to fiddle around. Okay, one more quick pass over this, looking for any other oddities from all of the refactoring I just did that can go away, like 100 plus 18. I think we're good. Okay, so the other thing is, if I'm making the edge know what its name is, then is it fair also to make the I-8224 know what it is? And I believe yes. Now, all these guys, I'm going to edge and hit them properly, but what I want to do is set their names to something under me. So I'm going to say phi1 arrow name is format %s underscore %s. And this is going to be my name and phi1 arrow name, like that. There. So whatever I initialize the name to here, which might have been, who knows, maybe we'll do something special. What I'm going to do is going to prefix it with my own name. So now notice that all of these signal names suddenly have gen in front of them, the ones that are owned by the gen at least. I think I can use sdiff to see what's going on here. Yeah, pretty much this is just put gen in front of the names owned by the gen, and this is what I wanted. Let's make sure that there was nothing at the end that looked weird. Okay, and that's modified so that I can, from a module like the 8224, I own edges, therefore I can set their name appropriately, and we can use common code to look at an edge and print it out based on the name. With the name prefixes, that gives me the ability to then go in and do things generically on edges and be able to identify where they are within the system, especially if it's a very large hierarchical system. And I think that is going to do it for the 8224. I think that probably rings it out. I could probably try sending in reset and ready signals with different timings and verify they are only trapped at the time I said. But given that they're coming out at the appropriate time and there isn't really complicated logic that might buffer that up and delay it, I believe that that is a good enough test. So let me grab Kraken again. And I am going to view the changes really quick. And I think what I'm going to do is add a new commit that said edge and I8224 have name fields. Is there anything else I am doing along with this? Also, only increment. Also, clock has no falling edges. Clock increments tau once per oscillator cycle. Those are significant alsos. Stage and commit and push. And you know, I think I am done for the day because I put in a number of extra sessions today and got a lot of good stuff done. I got my first actual, real, honest-to-goodness model going. Alas, I did not have time to set up anything to print out nice timing diagrams like that. So I can't actually compare timing diagrams, but we looked at the numbers and the numbers looked right. I have code that can do an ASCII timing diagram, but I would need to modify it greatly to go into this certain thing. So the next session, I believe, is going to be doing the 8228. Little taste of that to come up. Basically, it's that status strobe we produced. It's going to be taking that, plus some signals from the CPU. We've got a data bus. We've got a data bus input signal that says data is going toward the CPU. And if it's not set, it's going the other way. We've got a write pulse that says there's data coming out of the CPU. So dbin says I'm reading. Bar WR says I'm writing. HLDA is a hold system, which allows us to hold for DMA. And with those signals and latching the status byte from the CPU, the 8228 produces memory read, memory write, IO read, IO write, bus enable, and interrupt acknowledge. And it doesn't say so on this sheet very well. It kind of hints at it. Yeah, there it is in this paragraph. There is some extra logic in the gating array where if we do a interrupt acknowledge cycle, the CPU sends out an INTAC, but if it's a multi-byte instruction, the extra byte fetches are just normal memory reads from the CPU's point of view. And apparently the 8228 does something to turn those into int-A cycles. And I don't know how, but it does something to cause the PC to not increment inside the CPU. Or maybe the CPU has something special that does to not increment the CPU, despite those being memory cycles. We'll get to that when we do it. I will not be handling multi-byte interrupts on day one. In fact, when I handle them, I will be probably working deep within the 8080 and 8228 simulations to make them cooperate to make the right thing happen. And the signals going between them may or may not resemble the signals in the real CPU. So that's where we're going to start with the 8228, something real simple, mostly stateless. I mean, I'm going to capture the status and send it out when appropriate, but I'm not going to do anything real fancy with the INTAC cycles. Anyway, that's the heads up for next time. I'm going to give this a bit of a rest and go play some computer games. And I will see you all next time. Keep your code safe and keep